Hi, I'm Gordon Waite at Waite Research. My project for the next few minutes is to make a plastic keeper ring that is part of our mirror cells for our Renegade telescopes. This particular one is for a 12.5 inch, roughly f3.7, f3.8 telescope that I'm building for a friend down in Australia. So calling out hello to Brian and get a chance to see a little tiny part of your telescope getting built here. Well, the plastic keeper ring goes in the mirror cell, and its function is to keep the triangles that support the mirror evenly spaced. This is an 18-point mirror cell in this 12.5 inch telescope, and I need this little plastic ring to just simply keep those little triangles under control. With everything that we build that's CNC, we start with a CAD program. They're really simple to design here. You give it an inside diameter and you give it an outside diameter, so that defines the inside and the outside of the ring. Then within it there are 6 little holes that need to be drilled, and those are the 6 holes, one for each of the 6 triangles in the 18-point cell. Each triangle has 3 contact points, and what we're going to do is to use this plastic ring to tie together the inside point on each of those 6 triangles. So basically you give each one of these little circles a diameter, tell them to equally space them around there, give it the inside and the outside, and that's the basic design that we have. Now with CNC, this part is the CAD, computer-aided design. To get this to actually cut on the machine, you have to have what are called cut paths or tool paths. Now if we go over here on the software, I can bring up the tool paths for this piece, and here they are. And there's 3 tool paths, one to cut the little holes, one to cut the inside ring, and one to cut the outside ring. And basically each of those defines what tool you're going to use, how deep it's going to cut, what speed you're going to cut at. And if you bring up, you can show the edit on one of them. If you click on one, you can bring up and it shows the edit parameters, how deep it's going to be, what your start depth is, what the tool is, whether you want to go conventional cut or climb cut, all these things. So you define all these properties for this piece and then define all those tool paths, and when you've defined them all, you can combine up the ones that are all the same for a given cutting tool and make a final TAP file, TAP file, which actually gets downloaded to the CNC machine. So this computer, this is just a little Toshiba laptop that I use to control the machine. This little laptop really is the brains of the operation in that it grabs the CAD information and the cut paths off my server and downloads them into the controller for the machine itself. So this little laptop does all that work. So that's the setup for how I design and prep the part to be cut. Now we'll look at setting up the CNC machine to actually make this cut. Well, after all the CAD work is done and the cut paths and everything are all created and generated, then it's time to connect the laptop up to the CNC machine, up to the CNC controller, and actually get down to business. The control program here, this is the actual one that we use on our machine, and it really has 2 functions. The first function is kind of a setup function. There's what's called jogging, and with the jogger, what it allows you to do is to move the CNC machine manually here. I can move it, you can probably hear in the background, I can move it down, to the left, backwards, to the right, and move it up. And this particular piece of software also lets me set the 0 on the machine. So you can see over here, it shows the X, Y, and Z coordinates of the CNC machine. And when you get it to the 0 to define where you're going to start cutting, you set all these things and you can say, they're all 0 now. So that's part of the alignment procedure on the machine. The second part of this program is to actually load the cutting patterns from our server. And it's called G-code. G-code is the programming code that the CNC machine actually understands. So when you load up the G-code, you pick the file off our server, and this is all linked together through our normal network service through radio. So the server's in one building and this machine is in another building. So very cool there. So after I loaded the G-code, you see down here the pink area actually shows the G-code. If I scroll on it a little bit, these are the actual commands that will be sent out one by one to the machine. Now this is a very simple little piece of G-code. There's only 118 lines, but for the more complicated pieces, there may be tens of thousands, even hundreds of thousands of commands that get sent out to the computer. So after the G-code is loaded in the machine and the part is all set up and everything, you hit to run the file. It says press OK to begin the program. If I hit the OK there, the CNC router would actually execute and go and cut my part for me. So this little program running on the laptop is the controller that, or the source of control for the code for the CNC machine. Well, the first thing I'm going to do to prepare for this cut on the CNC machine is to install the bit in the router. The bit I'm going to use for this is just a little 1/8 inch router bit. It's just a little straight bit to flute, and it's all you need to cut through this ABS plastic. The plastic's only 10 thou thick, so there's no muscle required for this sort of cut. So basically we put this up in the router, and we'll move this out of the way for a sec. And I always just put my thumb at the depth that I want the bit to get loaded to, and go ahead and put that up in there. Tighten the nut up a bit. There's a little locking thing over here, and then tighten this up. And that's all there is to getting the bit in there. So we've got an 1/8 inch bit ready to go. Now if I lower the camera here just a bit, you'll see that the cutting surface here that I've got, this is called a spoil board. On my CNC machine I use MDF, medium density fiberboard, and this is a sacrificial board. When you make pieces, a lot of times you have to cut all the way through, and that by definition has to go into your spoil board. So this is just a piece that's on there to give a flat surface to work on. Now since I've been using this for quite a while, I've pretty much built a whole telescope on this one, cut a whole telescope. This one's getting all chewed up. So particularly for this nice thin plastic, I'd like a little better surface. So I grabbed a little piece of plywood, which is actually an old cutout from a previous piece that I made. I think I made the mirror cell ring out of this piece. So put that on there, and this has a nice flat top on it, and that will provide me a nicer surface for a spoil board. Now we have to lock this down, and we have little clamps all around the machine here to do just that. I'm going to pull this clamp out and move it up one onto the inside. There's all T-tracks on here, and all of the clamps run on T-tracks. Let me put that on, put it on the edge of the piece, screw that down. Got a couple more sitting here, so we'll put one over on this edge. Tie that one down. I'm going to put one more on here just to be good and safe. So now I've got an area here where I can cut on without any problem, and it's nice and smooth and flat. Now this is the material that we're going to be cutting. This is ABS plastic, 0.010 of an inch thick. It's nice and thin and flexible. And we need to mount this on here so that we can make the cut. Now ABS plastic, you cannot clamp it because it's just too thin and slippery. So instead, I'm going to use double-sided tape. And double-sided tape works real well for this. Basically, you just lay down sort of a bed of it. I'm going to have to get a pair of scissors here. So get a pair of scissors and just cut off pieces of this. And this is double-sided tape, or some people call it carpet tape. So basically, we'll just put that down on the surface. Make another one. Put that on there. And I'll throw one more small one on there just to make sure we've got good coverage on our circle. So there's our carpet tape laid down. Now the tricky part is, carpet tape has a cover on it to protect the sticky part, and you got to figure out a way to get that off. And it's supposed to be peel and stick, but mostly it's stick. You get that up, and it just peels right off then. It leaves you with the sticky area there. Next one, and the final one here. Trick is kind of just to pick an edge, and if you roll it against the backing, it's supposed to separate, but of course it's not so easy to do. Well, gonna mush a corner of it. Eventually you'll be able to get it up. Okay, now we have the sticky side up, and we're just going to take this ABS plastic, lay it in there, stick it down. And this carpet tape is really sticky. You don't have to worry about that coming up. And that's all there is to it. So now we've got the ABS plastic ready to cut. The next step is to pick a 0 point and set the router to the 0 point so it knows where to cut the piece. Now, roughly, I'm just going to stick the 0 point in here. So I'm going to use the computer to move the router down toward the point I want. Now the trickiest part is that you have to get the router bit to actually touch the top surface. And for that you get close and then you do what's called micro-stepping to get it perfect. And the trick is you do not want to jam the bit down into your material. It's hard to see how close you are, so you kind of have to look at the shadow and the reflection. And I'll go from slow to micro-stepping here so I can get a more accurate movement on it. I'm just going to drop it down 10 thou at a time until I can get her down onto the surface. And it looks pretty close. You know, it's pretty good. So now that position that the router's in becomes our 0 point. So I tell the CNC machine that that's the 0. And after I do that, I just go ahead and lift the router up just a little bit. And now we're pretty much ready to cut. The 0 that I chose is in the center of the rings, so I don't have to worry about any interference there. Now before I cut this loose, I check and make sure that all my clamps are good and that none of them are going to interfere with the cut. And I know my cut is about 7-8 inches here, so we should have no problem with that. Before I started, I cut the piece of ABS plastic to a generous dimension, so I know if none of my clamps are touching the ABS plastic and my router bit is roughly in the center, when I start the CNC cut, it's not going to get outside of the bounds that we've set there. So basically, this is ready to cut, and now it's time to do the business. cut's all done, so I'm going to lift the router up away from the piece. Now we can take off the clamps. And peel our plastic away. There's the outside of the piece. And with any luck here, we'll be able to get the ABS plastic off without bending it. And there's the final piece. It's got some plastic shavings on it, but that cleans up real easily. Now the cool part about doing this on the CNC machine is that it's so easy to customize it. Every different telescope, every Renegade that we build, we use the plot program to calculate the parameters of the mirror cell. So every single telescope, every single mirror has need for a different ring. These might be, a few thousandths of an inch off. And of course, different sized mirrors would have a different sized ring. So it's very quick to do this. You see the whole operation here was just a matter of a few minutes. And that's the huge advantage of having our own CNC machine to help us build these Renegade telescopes. So Brian down in Australia, there's your ring. And shortly, we'll have the rest of the telescope to go with it. Again, this is on really thin ABS plastic, and we just finished cutting it out on the CNC machine. And now it's time to install it in our mirror cell. I'll give you a quick tour of the mirror cell. We build this ourselves here at Waite Research. This is an 18-point mirror cell that's manufactured going into a 12.5-inch Renegade telescope. And the secret to our mirror cell is a bunch of spherical bearings, also called rod ends. The collimation attachment points are here, here, and here, and each of those is a spherical bearing in a rod end. And in the manufacture of the cell, this cell, the ring on the outside, is made in two parts. And then there's a threaded coupler embedded inside it when it's glued together. So there's threads in there, and the rod end just screws into the threaded rod. We use a template also cut by the CNC machine to be able to place this collimation hole at just the exact perfect place. So the whole mirror cell goes together to very exact dimensions because of having the CNC machine to put it together. So 3 spherical bearings there. Then each of the teeter-totters for the triangles is itself a spherical bearing. They're oriented up and down. These are oriented flat. So there's 3 bearings for the teeter-totters. And then underneath each of the triangles on the bottom side is another spherical bearing. This bolt drops down through a spherical bearing and then bolts firmly on the other side. And with all of these spherical bearings, all of these things are all loose, so that when the mirror is put on them, they all come up into a plane and support the mirror evenly on the 18 points. So this little keeper ring, the final little part to the puzzle, is mounted underneath one of the contact points on each one of the triangles. So that's the job that I've got to do right now. And basically the mirror rides on, each triangle has 3 little bolts. And these are made out of nylon, and they're really slippery. So basically we just need to run a bolt through the hole in the keeper ring and then screw it into the corresponding hole on the triangle. Whoa. Of course, the downside of this is everything is slippery. So we'll roll that 1/4-inch bolt through there, and all of the triangles, the holes are all tapped and threaded to take these bolts. So we just screw that in there. Now the trick to this, if you've ever made a mirror cell like this, it's kind of difficult to get all the dimensions perfect to get this ring to fit properly, because every one of these 6 triangles has to be at the perfect spot or the thing won't go together properly. So again, having the CNC machine to do all the cutting ensures that everything is perfectly positioned and makes this entire thing very easy to put together. And the final one. And look at that. The holes right underneath the ring. Now the one thing, the reason that we use this thin ABS plastic, it's very, very strong, but it's it's very flexible. So you can see that I can bend this just easily with a fingertip. And because it's so flexible, it doesn't affect the positioning of the triangles themselves. The only reason that this little keeper ring is in there is to keep the triangles oriented in the right direction, so that when you take off the mirror or put the mirror on, the triangles will stay where they need to be and provide you the support that you need. So now if I can lift this up, you can see that all of the triangles stay in the right direction. If that ring wasn't on there, they'd all be flip-flopping around because they're so loose on the spherical bearings. If I flip this over, you can see the back side. And again, these are the spherical bearings that are underneath the triangles. So a lot of spherical bearings in there, but it really makes for a nice mirror cell that is very, has the motion that you require and the freedom that you want to have on the mirror cell. But when you put the mirror on there, it locks down and everything is exactly where it needs to be. So that's how we do the keeper ring and Waite Research mirror cell, and another little part on a Renegade Telescope.